Hi, everyone. Thanks so much for welcoming me to this meeting. I'm new to this community. I'm an organic geochemist, and I work broadly in life detection, which probably isn't a typical topic at this meeting. But I do work with some authentic lunar scientists, Prabal Saxena and Nat Curran on this work, as well as contamination control folks at Goddard and Johnson, and even our own Andy Needham. And I'm going to be trying to break our conception of the lunar surface as being completely inhospitable to life, and describe what I mean by habitable niche here. So yes, I wanted to talk a little bit about this idea we have that open space of the lunar surface isn't a place where organisms could survive, because actually we have a lot of evidence from experiments on the ISS and other platforms and extraplanetary locations that there are certain microorganisms that can actually weather those temperature changes and those pressure changes and do maybe not thrive, but do okay. And we know that many of these organisms are things that can actually survive the kind of bioburden reduction protocols that we put our spacecraft through when we're trying to clean them before we send them to places. I also want to point out that many of these microbes are not what we think of as rare, special extremophiles like you might see on Nova or something interesting like that. They're what we would call cosmopolitan microbes. This doesn't mean they sit around in smoking jackets with martinis, but rather that they are everywhere. They are on you right now. And so that means that when we go to special places like the surface of the moon, we're likely to take them with us. These organisms, many of them have special adaptations to help them survive these conditions. And in our abstract, we talk in a little bit more detail about what those things are. But I wanted to approach this idea of survivability a little bit more to make sure that we're not thinking of things like massive growth happening on the lunar surface that would turn it into something like a dorm room fridge. So I want to kind of present this idea of survivability in what I call the scale of lifiness, with a rock at one end and the dorm room fridge on the other. And many of the things that I'm going to be talking about that could survive on the lunar surface are actually farther towards this rock or not so alive end of things. And this would be something like a virus, which is something that can't reproduce on its own without you or me or one of our cells doing some work for them, or something like a spore. A spore is actually a lifeboat that a cell sends out when times get tough and there's a lot of something like a nutrient reduction. And that spore can basically hang out in an area waiting for times to get good where it can go through growth again. So this is this idea of survival and growth, and we're going to be talking mostly about on the survival end of cells, not necessarily the growth end. So yes, with that idea, I do want to remind everyone, and many of you are familiar with all of the many ways that we have seen in modeling work that the moon surface can be lethal. I love the way they talk about this in roughly descending lethality. So yeah, the high temperatures, the big temperature swings, all of those things are things that can destroy cells, the UV radiation and energetic particle radiation, of course, and of course the very low pressure, the vacuum of space. These are all things that would affect growth and in some cases survival of spores and cells. But what is not necessarily represented by this modeling work is the effect of topography or surface roughness that might lend certain locations on the moon a little bit of a habitat or shelter for these cells. So again, to paraphrase Lord Elton John, the moon ain't no place to raise a family. But here's what we're talking about when we talk about topography and surface roughness, is this idea that with the very low angle of the sun and the very rough surface that we are now becoming aware of with all of this new data that I think actually Julie's talk did a great job of showing us in a very dynamic way that with that movie, that there would actually be a lot of shadowed regions where some of those lethal things like temperature shifts would not necessarily be a big problem here, and also the radiation effects. So what we've done in our work is we've taken LOLA data and digital elevation models, and we thought about each of those biocidal or lethal features of the moon and tried to map them in a spatial context to understand where in the places that we would like to explore some of these features are worse or better for survival or growth of cells. And so you can see that there's a lot of locations that have relatively low maximum summer temperatures. There's certainly evidence for surface and subsurface water from the polar water equivalent hydrogen that we've mapped. And then when we look at the surface roughness, we can start to see how that relates to, again, the shadowed regions, which confer some of that temperature variation, survivability, as well as protection from radiation and energetic particles. That's also seen here in what we're calling the sun visibility fraction, which is showing us very dramatically some of the shadowed regions. So these are all shelters for any microbes that we might take along with us. Where me and the microbiologists that we work with come in is we started thinking about all of those taxa of microbes that we know can either survive in space conditions or we know are able to survive our efforts to kill them in spacecraft assembly areas. The kinds of organisms that even if we haven't found them in space, we know that they have the same features that will lend survivability. And we've tried to think about all of their different parameters of survivability in the context of those maps to understand where these taxa might actually be able to survive on the lunar surface. And so here's a map showing the survival regions for the very cosmopolitan bacteria Bacillus subtilis, which we all have on us right now. And it shows you in relationship to the areas we're all interested in with Artemis, where this bacteria would likely be able to find a micro niche where it could survive. Again, this is an organism that's 2 to 6 microns big, so it doesn't need a lot of space for it to hang out and become part of this landscape, which could certainly affect some of our science objectives and the measurements that we would like to make if this spore is where we're looking. So yes, here we're just seeing, again, the areas in pink are where it would actually survive. So just in conclusion, I wanted to say that where our work is going with all of this is that we're going to try and imagine a conception of a map for many of the cosmopolitan microbes that we're talking about and see the areas of survivability for all of the candidate sites. And we would just want to use this as a way to think about the kind of contamination control we would want for exploration, as well as maybe a way to think about the kind of measurements you would want to make at a particularly survivable site, especially if you're thinking about volatiles or light element analysis. I think also if we were trying to prevent something like a growth scenario, we would also want to think about things that Jenna was talking about. So for example, if we're going to a place where there's a likelihood that the volatile toluene could stick around, that would represent a carbon source that could help move our microbes from the survival side of the lifiness scale into the growth side of the lifiness scale. So with all of this, we do have a paper in the works, and I'm very interested to hear your thoughts on this as end consumers of this effort, since we're still in preparation of that manuscript.